Right, so this is it's based on joint work with Manik Dar, who's a grad student in Princeton, and Ben Lund, who's a postdoc here. So let me start with the definition of what is a Furstenberg set, and then we can talk about the connection to the Kakeya problem and so on. So it's as Irit said, it's a generalization. So so you have a set, say S in fq to the n, where fq is some finite field. And we say that this set is Km Furstenberg if you take any k-dimensional subspace, if for all dimensional subspaces, say U in fq to the n, you can take this subspace and shift it so that it has large intersection with your set. So there exists some shift A such that if you take U and you shift it by A, this is shift, it intersects S in, there's one parameter I wouldn't use, it's M, so it's in at least M points. Let's say if you draw a picture, you'd have, this is your S, this is the origin. So a subspace U is, let's say, a plane through the origin. You can add some vector A such that if after this shift, there are at least M points here. You can do it for any such. So the subspace through the origin is like the direction of the shifted subspace. Okay? So it means that these are sets that have large intersection with a subspace in every direction. And the parameter M is somewhere between 1 and q to the k, where q to the k is just a number of points on a k-dimensional subspace. Yeah. So the question is, how small can these sets be? And let's just make a little definition. Let's call this fkm is the smallest size of such a set, where S is Km Furstenberg. And there are two more parameters that I could include here. It's Q and N, which also play a role, but just keep it simple for now. The two important ones are K, the dimension, and M is the intersection. And the kind of the famous special case of this that was studied before is the finite field Kakeya problem, which corresponds to the case that, so K is 1, so you're dealing with lines in every direction, and your set has to contain each line. So these are sets containing lines in every direction. And this problem has a long, fascinating history, starting with 100 years ago with problems in Euclidean space, sets with that contain a unit line segment in every direction in R2. And then there's the finite field version, and there was a lot of interest in it in connection to other problems. And somewhere around 10 years ago, there was significant progress on it. So I'll mention two papers. One is, as Irit says, it was when I was a grad student, and this was a joint work with Kopari Saraf in Sudan a year later. And basically, we kind of know the answer for this setting now. So every such set, so if you contain a line in every direction, you have to be of size at least q to the n over 2 to the n. And there are constructions of such sets that have size q to the n over 2 to the n minus 1. So somehow, before this works, even the exponent wasn't known, and we went from not knowing the exponent to knowing the size up to a factor of 2. That if anybody wants to close it, they'll be much appreciated. It's right. And so this is when you're containing a line in every direction. But the proof technique, which I'll discuss in a minute, actually works for any m. So let me just say, so the name Kakeya refers to when m is equal to k. This is called the Kakeya problem. When m is, or when m is equal to q to the k. And when m is small, it's called the Furstenberg problem. So this indicates it comes from different problems in Euclidean space. One is called the Kakeya problem. One is called the Furstenberg problem. But it's just a matter of why is it called Furstenberg and not Kakeya. So it's because m is small. So the same proof here.
Is when m is equal to q to the k.
Yeah, exactly. Yeah, you're containing everything. And then Furstenberg is for general m. So the same proof here gives essentially the same bound with the same constant, just m instead of q. And you would think that the upper bound would be the same. So it's not clear actually what the upper bound here, and it seems to depend on the field. So when m is small, this becomes a much more difficult problem. So if you don't assume anything about the field, then up to some constant here, you can get m to the n with some constant depending on n. And this is an example of Wolf, and it's generalized to high dimension by Zhang, which is maybe 16 or 17. And again, this requires m to be some square root of the field size, and you need a subfield of that size. So the field has to have has to be of square order. And then for other fields, there's some conjectures that it should be that this should actually be much stronger for, let's say, if there are no subfields. So this is a whole really difficult open problem that even in one dimension we don't really understand all the way.
So if it was a prime field, for example?
Right. So the conjecture is that this should be, so let's say when m is, the conjecture that's stated when m is, let's say, q to the 1/2, this should be q to the 3/4 n. So see, it's bigger than m to the n. So there's a construction that gives this for prime fields. When q is prime,
Upper bound.
there's an upper bound that gives this, and the conjecture that it's tight, and the known bound is maybe slightly bigger than this, but not by much. So it seems to be related to things like sum product, and when you have subfields and you don't have subfields, and it's a very, very nice question. But we won't talk about it. We'll talk about the high-dimensional case, the k bigger than 1. Maybe before that, let me say what is the method here, and why does it fail for q equals 2. So this result used the polynomial method. Which has, roughly speaking, three steps. The first step is you assume that assume by contradiction that S is small, and you say, okay, if it's small, then there's a polynomial of low degree that vanishes on it. So there exists some low degree polynomial f such that f vanishes at all points in S. And you can get the degree here to be something like, well, as you expect, less than m. And then you restrict f to, so you have a line in every direction that intersects your set. So it means that f has more than m zeros, or at least m zeros on the line in every direction. So So if you restrict f to a line, it still has degree at most, its original degree. Right? Restricting to a line cannot increase the degree. And then there are m zeros on this line. So polynomial of degree less than m cannot have m zeros unless it's identically 0. So you get that f vanishes identically on a line in each direction. So from having m zeros on S, you get that all the other points must be 0. And then stage 3 is you piece all these pieces of information together to get some contradiction that you get that f is identically 0. Because if it vanishes identically on a line in every direction, somehow there's too many constraints on f, and you can show that the only solution is 0. So this is not so important. The important thing is step 2, which fails when k is bigger than 1. So any questions? Or? Yeah?
Yeah, so one question up there. When m is, say, q minus 1, can you get some good bounds?
When m is q minus 1. Yeah, when m is close to q, the polynomial method. Yeah, I was just about to say why this fails and say that it kind of works when m is very close to q, but it fails when it's
hard cut at m equals q. Okay, good.
Yeah, there's no hard, yeah. But let's just say why does this fail? So let's say instead of lines, you have a two-dimensional plane. I guess just write it this way. And let's say there are m points of intersection of your plane with S. If m is relatively large, if it's close to q squared, then you can still say the polynomial cannot have too many zeros on the plane. But you can have a non-zero polynomial f. Just write it this way. Right. F can have. How many zeros can f have on a k-dimensional flat? Anybody remembers?
What is a flat?
A k-dimensional, a shifted subspace is a flat. Yeah, so it can have you take its degree and you multiply it by q to the k minus 1. For example, if f is a product of, if it's degree d and it's a product of d linear forms, it will have exactly dq to the k minus 1 zeros. Yeah, up minus the origin, whatever.
Minus intersection.
Okay, yeah, but roughly that. Oh, you can take them in parallel.
Oh.
You take parallel. In the plane, you can take d parallel lines, and you'll get exactly. So this is tight. You can achieve this. This is called the Schwarz-Zippel lemma. That you cannot do more than that. But this is not very good, because if m is bigger than this, so it has to be much bigger than q to the k minus 1, and then this method can give you something. But if m is small, let's say, for example, if m is something like q to the 2/3 k, you expect to get some bound on sets with this m, and this doesn't give you anything. Right. So let me first mention results that are known. Yeah.
Can you give some intuition? Why would we expect when m is q to the 2/3 k?
What do you expect to get?
Yeah.
That's coming up. Let me just say what we know when m is exactly q to the k, or almost q to the k. So this is the paper of Ellenberg, Oberlin, and Tau from 2010. They did a lot of things in this paper. This was just one of them, and there's another paper of Kopardi, Lev, Saraf, and Sudan from 2011, where they dealt with a case where any k, and m is equal q to the k. So this is the high-dimensional Kakeya problem. Right? So you have you're containing a flat in each direction. And they showed falling bounds and so it's there. So some constant times q to the n, and so it's a construction, and the lower bound is another constant, q minus 1, k. So if you ignore these things, so when q is large enough, which is the case in some of the applications, when q is large enough, these constants approach 1. So you get almost all the points. So this is even stronger than the Kakeya bound, where you have this constant 2 to the n that's really the right constant, or at least up to 2. When k is at least 2, even when k is 2, and you take the field to be large enough, this 2 to the minus n constant becomes essentially 1. You get almost all the points. And this, again, uses the polynomial method, and so it does work in this case, and you can get more out of it, because every vanishing on every plane gives you more information, so you can take advantage of that. Okay? All right, so now for the general case, and try to answer Irit's question, what do you expect? So, or why should you get something? All right, so now general k and m. So let me say that first the result that was prior to this work. This was Ellenberg and Ehrman in 2016. They showed lower bound of some constant depending on n and k times m to the n over k. And typically people think of small n here, kind of even fixed dimension. So that's why you can think of these things as a constant. But in applications, and I didn't mention it, but these results had a lot of applications in theoretical computer science and pseudorandomness. You care about n. N is not a fixed constant, so you care about this constant. They didn't really care, but if you look carefully at their proof, you get something like this. 1 over n, n log n over k. Okay. So it's not a great constant, but the important thing is the exponent here. So if you think about it, m is between, right, 1 and q to the k. So to answer your question, if m is q to the 2/3 k, you expect this to be q to the 2/3 n. And okay.
Does that answer my question?
I don't know. That's why I paused. So if it doesn't,
Can you explain
okay. So
intuitively
is there an upper bound, right?
what you would expect, or you know?
Okay. So we still even after this talk, it's still open to find. So okay,
I'm not asking for an exact thing. I just want to.
we'll get an exact answer for large fields, and for small fields, we still don't really know.
Okay, but why would you expect?
Well, if you take a small example and tensor it somehow, which doesn't work, but if you could make it work, then it would somehow the exponent would carry over to the. I mean, that's my intuition. Why? I mean, if this is the right answer, then it might come from something like this, where you have a small example that tensors maybe. So, but yeah, maybe. Okay. We'll see an equivalent formulation of this using kind of mean entropy, and there's something about like entropy rate that stays the same and things like that. So maybe that will explain it more. But the real answer is that for general K and M, we don't know the upper bound. For small fields. For large fields, now we know. So, and it's not this, it's something else. So anyway, just kind of, you can ask again at the end, and so this paper was the first to give something for general N and K, and you might wonder how they did it. And the answer is that they did it using schemes, which is the language of kind of modern algebraic geometry. So they generalized this problem. They proved something much stronger. There's something that generalizes finite sets in FQ to the N. It's like zero-dimensional schemes supported at the origin, or just zero-dimensional schemes in general. You can generalize this for zero-dimensional schemes, which in particular include finite sets. And they prove something much stronger, and they use very sophisticated methods, and there's some polynomial methods in there, but there's a lot of other stuff. So this was, when I first saw this, I couldn't understand it at all. Yeah?
Did you need schemes? Like, is there really something you can prove about, finite fields with schemes that you can't prove in an elementary way? Like,
good question. So I'll answer this. So okay. So first thing we saw this, and we couldn't. I couldn't understand anything. Eventually, Manik came from a master's in Stanford, and he knew enough algebraic geometry so to kind of work through it, and we could. With Ben, we understood it, and we actually wrote this up just now, just before we found this simple proof that I'll show you. We did this in an elementary way. But it's the same proof, just using language that of polynomials and ideals, which we could kind of follow. And we also improved the constant to which is tight for schemes. At least maybe not the 1/16, but a constant to this thing is tight for schemes. But there's really beautiful stuff in here, but luckily, just after finishing this up, we realized that much simpler proofs with better parameters. So this is this work. So there are two theorems. One is for general K and M. And we get 2 to the minus n m n over k. And the other one, when m is sufficiently large, so when m is bigger than, let's say, 2 to the n minus k plus 7 q over epsilon squared, fkm, this 1 minus epsilon m q to the n minus k. So okay, so now we're coming. This bound looks a lot different than this bound. It's much better. And just to see how, okay, so we're assuming m is large enough. There's some 2 to the n here, and q and epsilon. And if you look at it, so if m is at least 2 to the n q, then in particular q has to be pretty large. So this is for large fields, okay? Which is kind of the case that was originally kind of the most studied case, but again, for applications, which this still doesn't have, but it might have, this might be important. So again, just to say why this is a good bound, so there's a trivial upper bound of m q to the n minus k. So anybody can come up with a set of this size that will have m points intersection with every shift of every.
And parallel planes of n minus
So it's so trivial. The answer is actually any set. Any set of this size is a k and Furstenberg set.
Wait, what?
Yeah, take this set like this. Take any k-dimensional subspace and look at all of its shifts. Right? They're disjoint. One of them has to have at least m points by averaging. Yeah. So when q is large and k is at least 2, I should write this here. This is, yeah. This is very important. So once you go from k equals 1 to k equals 2, if you're over a large enough field, there's something very different is happening. So there's just no interesting examples. Any set somehow, and any set of non-trivial size will not have this property. So the answer, the general answer might be closer to this, but somehow when the field is small enough, I mean, it could be something like this where the epsilon depends on the field size. When the field gets large, epsilon goes to 0. So this could be the...
So is that easier to prove? It seems like
This?
second one?
Well, both of these are easy. Relatively easy. I mean, much easier than this. They both have one or two ideas. And I have half an hour. I'll show you both, hopefully. So, any other questions? I'll show you a sketch of both and without the details. All right. OK. And as I said, this doesn't have applications yet, but still thinking about it. Even this took a while until we had kind of applications for extractors and things like that. So, all right. Yeah. I think we can remember the definition.
So somehow the characteristic doesn't play a role in any of these numbers?
Well, it might. We don't know. So again, there's this upper bound here depends on the subfields. There might be an upper bound, and I've been thinking about this yesterday, not just yesterday, but especially yesterday for a few hours. My flight was delayed, so I was in an airport. I tried to see if this construction here generalizes to higher dimensions. If you have some subfields, and maybe the subfield says other subfields. I couldn't make it work. So there might be some dependence. And it might be that with subfields is the upper one, and without subfields is the bottom one. All right. So let's do the proof of 1. The proof comes from, it starts with giving an equivalent statement of this theorem. And then hopefully that will be easier to prove by kind of induction on k. So we're trying to reduce to k equals 1. Both of these in some sense do that. So let me write two statements. Statement 1 is what we want to prove, that if S is Km Furstenberg, okay, now okay, I'll write something here in a second. Then S is at least C and K M over K. So C and K now, it will be a parameter, so it will be some relationship to some other parameters. And the second statement requires a definition of mean entropy, which you might know, but I'm sure some of you don't. So let me write it here so that if you have a random variable, x distributed on fq to the n, we can define the q mean entropy of x is the following thing. So it's denoted h infinity q. It's what is it? It's minus log base q of the maximum over a probability that x is equal to a. And a is anything in the support of x, because we don't want this to be 0. So if you've never seen this before, it's a very simple thing. You look at the distribution of x. So this is now if this is a, this is the probability of getting the value a. You look at the L infinity norm of this. So you look at the maximum value, right? So if this maximum value is q to the r, q to the minus r, then the mean entropy is r. So you should take minus log of the maximum value. So if this thing is large, it means that the distribution is very flat. Then nothing is obtained with high probability. So the higher this thing is, the better, the more randomness you have. So it's a very strong notion of entropy. If you think of Shannon's entropy as like an average entropy, you look at all the value, the average probability. Here you look at the maximum one. So if this is large, then all the other entropies, including Shannon's entropy, also have to be large. Okay. And just we pick q here because we look at distributions on fq to the n. It'll just easier to look at q. So this thing is between it's between 0 and n. And then you can define also the entropy rate as h infinity q over n. So this is just a number between 0 and 1, which is higher for more random variables. Okay. Any questions on this? In extractors, we use this all the time. If you've never seen it before, it could be a little tricky. But it turns out to be really the right thing, the right way to look at these problems. Because there's this maximum here, and there's also a maximum there. You're looking at all shifts of a subspace. So it works nice together. So let me use this definition to give an equivalent statement. So for every delta, if S is a subset of fq to the n of size q to the delta n, then there exists an onto linear map phi from fq to the n to fq to the n minus k, such that the mean entropy of phi of, so I want to take the random variable uniform on S. So let's call it US. This is uniform on S. Is at least delta times n minus k minus some constant dnk. Okay, just parse this for a second. Take any delta. If you take a set of size q to the delta n, any set is of size q to the delta n for some delta. No, it doesn't have to be like some rational or anything. Then you can find a linear map that reduces the dimension by k, right? But keeps enough mean entropy. It doesn't lose. So you're starting with mean entropy rate delta, and you output something of mean entropy rate also delta, but with some loss. And the loss here will be connected to that constant. Yeah.
Can you say something about how you find such a linear map?
Yes. Yeah. Well, I'll prove it. It's not. Yeah, it's not random. So maybe you see it already, but okay, I claim that these things are equivalent. So let's prove one direction. That's the one we're actually using, the only one we'll use. So the claim, or that one is if and only if 2. And there's a equation connecting the constants. C and K is q to the minus n over k d and k. So let's show the proof of 2 implies 1. It's a little surprising, but kind of once you see the proof, you realize it's not there's nothing very deep about it. Just the definition is the right one. So we're assuming 2 holds, and we're trying to prove a lower bound on Furstenberg set. So let S n be Km Furstenberg. Okay, so let's consider some onto linear map. Let phi q to the n minus f q to the n minus k be some onto linear map. So what does these two things have to do with each other? So think of
Some or the one that you have?
no. I'll say something about. I'll show that for any phi, any phi. I like to say phi. It's probably the wrong thing, but for any phi, this is small, and then we'll conclude something about delta. So let phi be some map. What is the mean entropy of this thing? You take a uniform distribution on S, and you map it down. So let's draw a picture. This is fq to the n, and this is fq to the n minus k. Right, so how do the preimages of points here look like? There are k-dimensional subspaces, right? So the preimage of 0 is some subspace U of dimension k, and all the other preimages are shifts of U. And what's the probability of getting a point here? It's the intersection of this, your set S, with the preimage of the point, divided by the size of the set. So I know that for any U, there's a shift with many points. So it means that for any phi, there is low mean entropy. Right? So this is at most minus log q m over s. So there's some value with this probability. Okay. So the mean entropy cannot be too large. So now we just have to plug that in and see what it tells us about the size of S. That's an easy calculation. So we'd like that thing here. You'd like to take delta such that this thing is delta n minus k minus d n k. Okay. So delta is something like this. And you have to worry about this being less than 0 or bigger than 1, but you have to do the calculation and see that that's OK. Everything works out. So because we're assuming 2 holds, and we have an upper bound on the mean entropy, then it must so it gives an upper bound on S. So by 2, we know that S has to be at most q to the delta n. Why? If it was bigger, then it would be equal to q to the delta prime n for some bigger delta, for delta prime bigger than delta, and then you would get a contradiction. You get something with higher mean entropy than this. OK, so you plug this in here. There's S on both sides. You move it around, and you get that S is at most. I'll save you the calculation. You get the bound you need. It's just you plug this delta in here. The log q and the q kind of collapse. You get some power. You have S here. You get S to the 1 over n minus k on the other side. Yeah.
Doesn't the inequality should go the other way?
Oh, sorry. Yeah. Yes. Yeah, it's confusing because you get an upper bound here. So you expect it to be an upper bound on S here. But because there's a power of S on the other side, it flips around. Okay. Trust me.
Convections also basically describe that.
Yeah, it's the same thing. Really nothing clever. It's just a nice, I mean, for someone who started his career doing extractors, this is like a very extractor-like statement. It's something about linear maps being good condensers. So you can really think of this as a completely separate statement that you would be interested in if you're doing pseudorandomness. And
What I missed somehow is
Yeah.
where is the shift happening?
the shift is the mean entropy says, look at all the points in your distribution. What's the probability of getting that point? So what's the probability of getting once you fix phi, you fix a subspace. That's phi minus 1 of 0.
Oh, and then the different points are the different shifts.
They're just the shifts. Yeah. Other questions? All right. So, OK, so why is it better? So did we gain anything going to 2? So no, not really, because it's equivalent, right? But this gives you an idea how to prove k, the general k for k equals 1. You say, OK, I'll start with my distribution on S. I want to show that there exists a mapping phi from n to n minus k. So let's first show that there's a mapping from n to n minus 1. Let's call it phi 1. That keeps a lot of the entropy. This would be phi of S. And then find another, this would be phi 1 of S. And find phi 2, applying the k equals 1 case again. And keep going k times. And there will be some loss in each step. And hopefully they'll add up to the right thing.
So are you using now the fact that 1 implied 2 and the Kakeya in the case k1?
Yeah, we'll see in a second. I won't use it. But you might. If you could prove this by induction, then you would also need the other case to prove the k equals 1 case. But we'll see. We'll have to generalize this one a little bit. And then we'll. But just to get the idea. So when you first see it, say, OK, yeah, if these are equivalent, as you said, then you can prove the k equals 1 case, and then apply it k times, and then go back. What's the problem with this? Why doesn't this work? So this has to be a uniform distribution on a set. Once you apply phi 1, it's no longer a uniform distribution on a set, especially if you keep going. It'll be some distribution. OK, so we just have to change this. And I want to have some time to talk about theorem 2. So let me just give you the very high-level sketch. It's just it's the same. as 2 with an arbitrary random variable. So basically, you get something like so you have some, this is the delta, the original one. You get the same one with a loss for any random variable. Yeah.
Where's this existential thing? So one and two are equivalent, but somehow there's this mysterious existential quantifier too, which doesn't appear in one.
Well, it's the counterpositive. I mean, this tells you that for every subspace there's a shift, and this tells you that there exists a linear map with.
Okay, cool.
Yeah.
Okay.
Okay, so anyway, so this is a stronger version. Obviously, it implies 1 for any k. And you can prove the k equal 1 case of this using the polynomial method. It's just, and it's something that was kind of implicitly, the method is just looking at the distribution and doing the polynomial method with multiplicities, where the multiplicities are chosen according to the weights of the points. So this was done by Ellenberg, Oberlin, and Tau, which were on the board before, to prove something slightly different, but it's essentially kind of, this is not very new. And once you have it, you prove it. This just carries through by induction, and you get the right. You get this 2 to the minus n. So this d turns out to be something like log base q of 2, and which translates into 2 to the n in the thing. Okay. So any questions before I switch to theorem 2? All right.
So this word you get from?
The what? The
Going to show us this? Or
to show what?
how to construct phi that
Oh, given a set, how do you find such a phi? I don't know. I didn't think about it. I mean, I don't know if there's a reason. Like, I mean,
Is a one-dimensional thing constructor?
it's not clear if it's if it might be NP hard or something. I don't know. And I've never thought about it. I really don't know. And if k is small, you could just try all of them. That's, No, I mean, okay. So maybe you just you do it for k equals 1, and then you can search. No, actually, you can't even search for k equals 1. It's q to the n, right? It's q to the n linear form, linear projections.
fix the basis.
If you can do k equals 1, then you can kind of keep going. I don't know. All right.
The random one never works.
I think that the random one shouldn't work. I mean, it will give you something, but maybe not as good. But yeah, I'm not sure. I really don't know.
So,
We did this just to prove something. We don't really. But it,
independently very interesting.
yeah, good.
So if you're looking for tight examples.
Exactly. So tight examples might be easier to think about this as distributions. So yeah, there are a lot of interesting open problems here. Right. So okay, good. So I have enough time to give you the idea, I think, of the second one. Okay, so probably go a few minutes over time. So let's think about the k equals 2k's, and everything else, everything will generalize to any k. Now the field is large. Okay, so here's the main, one of the two main lemmas that's kind of maybe of also independent interest is the following. If you take two flats, you take R, a family of two-dimensional flats. Yeah, a flat for me is, again, it's a shift of a subspace. So just an affine, you can do an affine subspace. Flats in all directions. So in the general problem, we have a set that intersects all of these in m points. But let's just look at this family without any set. Just take a family of two-dimensional flats in all directions. And you look at all the lines that are contained in one of them. Then, if you take their union, actually, I don't want to take the union. I want to take, then for each one, you look at all the lines that it contains. And together, you get a constant fraction. You get a big fraction of the lines. And they contain 2 to the minus n minus 1 fraction of all lines. So I'll draw this as a picture with simplicial complex explanation. So if you look at all the points, all the lines, and all the two flats.
And the lines also with cubes?
Yeah, all lines. Yeah, these are all lines, all points, all two flats, right? If you take any set here that has all directions, and you connect each two flat to all the lines inside of it. It's like a simplicial complex picture, right? These are the two cells. These are the one cells, whatever. Then the set of neighbors. This will have at least 2 to the minus n minus 1 density here. And we know that the same thing also holds here. This is just the one-dimensional Kakeya thing, right? If you have a set here in all directions, then it has 2 to the minus n fraction on the side, on that side. That's the one-dimensional Kakeya thing. Okay, so what I'm saying is that the same thing happens at all the levels. If you look at k flats in all directions, you look at all the k minus 1 flats, you get a constant fraction of them, 2 minus n minus k fraction. Okay, I have room there. So the proof of this is it's a pretty simple reduction to the one-dimensional case. You could just proof by picture. So take any n minus 1 flat, n minus 1 dimensional subspace. Let's call it H. And let's say it has a, so OK, we're on a finite field, so there's no such thing as orthogonal complement. But let's just pretend that there is for a second. So take this, you can replace it with something that behaves in the same way. So take some v and take everything orthogonal to v. And now look at all of these wi's that are perpendicular to v. So if you shift them to the origin, they'll contain v. Right, so
You take n minus 1 dimensional subspace.
yeah,
Wi needs
you do this, right? And then you take all of these that are perpendicular to this direction. So they still have 1 degree of freedom.
Perpendicular would be.
Sorry, not perpendicular, a parallel.
Okay.
Sorry, parallel to v, and then they can still shift. Okay. They can still rotate. So each one intersects this h in a line, right? If this is one of the wi's, right? This will be another one. So the set of these lines will have all directions in h. So it will be a Kakeya set. So it has to have 2 to the minus n fraction here of the points in h. But then we had everything above it. So you you have 2 to the minus n fraction of the lines perpendicular to h, and then you do it for any h. So you get something even stronger. You get for every direction, you have a 2 to the minus n fraction of the lines in that direction. Okay, so that's okay. So why is this good? So this is a high-level idea of the rest of the proof. So we're trying to say that if something has large intersection with all flats, then it's if in flats in all directions, then it's large. If we didn't have this condition on all directions, if we just said that a set has large intersection with almost all of the k-flats, then we know it's large. That's like standard sampling argument, like the expander mixing lemma or whatever, Cauchy-Schwarz, whatever you want to call it. So the idea is to start here, saying you have these flats in all directions. You take one step here, and you see that in each of these, okay, so you have your set S, and you have these WIs. Okay. In each WI, I have m points. So if I take a random line in WI, if I take a random line in WI, it will intersect my set S. So what's the expected intersection? It's so I'm sampling with density kind of 1 over q. So I expect to see something like m over q points here. So let's look at WI. Right? So it's a 2-dimensional flat that has m points in S. Now take a random line. You expect, the expectation is this. And we know that it will be concentrated around the expectation if the field is large enough. Okay, and we know that the field is large enough, so it will be concentrated. So there'll be very few lines that deviate from this by, I don't know, 1 minus epsilon. But, so I did this for every WI. I throw away all the lines that have small intersection. So I have almost all the lines here. No, not almost all, but I have a constant fraction, 2 to the minus n fraction of the lines. And I threw away a small fraction, even smaller fraction. So I still have a lot of lines with large intersection. And then I apply the same sampling argument on the entire space, and I get that. So basically, in each WI, I have few bad lines. So m over q 1 minus epsilon. So by the lemma, by this lemma, there exists, so here we have 2 to the minus n over 2 fraction, but so maybe half of them are bad, so the other half will be good. So there exists at least 2 to the minus n good lines in the union of WI. So, right? So good here, they have large intersection. And then you apply the same sampling thing. So you're saying S must be large. Right, so we went from S having large intersection with 2 flats in every direction to S having large intersection with many lines. So like a big fraction of the lines. So it's a much, much easier problem. Right. So that's it. And I think I mentioned the open problem. So this gives a very tight bound on basically when k is 2, right? There's no interesting examples, but when q is small and there are subfields, I mean, it'll be nice to understand what the right thing is. We still don't know what happens when the field is small, which is interesting, could be interesting applications.
When the field is small, the thing that goes wrong in this argument is some of the sampling or the
sampling doesn't work. Maybe it works on average somehow. Maybe you can control it better. But if you just look at a 2 flat, I mean, it could have, right, 20, less than 20, so 25 points. What do you do? Maybe with high-dimensional expanders, you can. There has to be something with high-dimensional expanders. Right, thank you.